Now that we've introduced the idea of the complex exponential, we want to bring that back to our analysis of the spring mass system. And again, the spring mass was a simple layout where we had a mass attached to a spring attached to a wall, and we were just studying how that motion could be predicted over time if we knew some fundamental properties like the spring constant and the mass associated with the mass at the end, the block at the end. It's tempting sometimes, though, to look at that block and go, ugh, who's predicting blocks? No one has blocks in even their designs for anything these days. Who cares? Well, engineers for massive buildings care. This is a 730-ton blob of steel, I presume. Actually, I didn't think to check the material. Steel or concrete. And it is at the top of Taipei 101, the second tallest building, I believe, now after the Burj Khalifa. And this pendulum acts essentially like a spring. Things swing back and forth. You can predict, you've got masses, you've got something that's equivalent to a spring constant in the length of the pendulum that's in there. And that mass helps to stop the tip of the building from moving back and forth in a way that would make users of the building very, very queasy. The math of that structure ties directly back to the mathematics of a spring mass system. So it is massively important on that scale. And it's also important too, just even at the simple level of your car and designing spring systems for shock absorbers. There's a spring, there's a damper. It is literally a spring mass system with a damper on it that is designed into your car's suspension system. Less obvious maybe, but typical as well, is that you have walls. Many of you in student housing may have already experienced this. If you have different kinds of wall structures, those walls can act as resonating cavities, very much like a spring mass system, and you can look at techniques of changing the mass or changing the stiffness of the material to determine what kinds of sounds will make it through those walls and be transmitted through it. So the spring mass is an idealized system that we use for inspiration, but the same mathematics shows up, in fact, sometimes the same physical system shows up in important areas in engineering design. So, with that motivating speech, let's take a look at our simple spring mass system again. This time, for variety, we've posed it as a vertical scenario. The key thing, though, doesn't actually change. If we look at the equilibrium position for the mass in the vertical position, it basically, having gravity in play, just shifts that equilibrium down a little bit to adjust for the force of gravity. But once we know that new equilibrium, all oscillations will happen equally around that center. So when you do your second year differential equation course, you'll find a much more nice mathematical way to prove that this force of gravity just shifts the equilibrium. For now, we'll just ask you to take it on faith. With that little caveat aside, if we take a look at our mass times acceleration equals forces, we go back to our differential equation. Whatever behavior is going to be exhibited by this mass, i.e. what x coordinate we're going to get over time, it's going to have to satisfy this equation, otherwise F doesn't equal ma. So to have our mass times acceleration equal the forces that are in play, we have to have mx double prime equals minus kx. Now what we're going to do is we're going to propose a solution to this equation. We're going to say, I don't know what x is, but I feel like it could be an exponential. In the back of your mind, hopefully you're remembering, actually it was a cos or a sine was the answer last time, but okay, sure. Let's try it with an exponential and see what happens. So this is a classic method in differential equation solving where we think we know the basic form of the answer. We're just trying to nail down A, if it works at all, and B, if it does, maybe only some specific values of lambda are going to work here. So what we're going to do is sub this into the equation and see what we get. So we're going to sub it in. We need to have x double prime. Well, x is equal to e to the lambda t. If that's our guess, then x prime is equal to lambda e to the lambda t. And I'll try to make my lambdas look different from my x's here to be very precise. And the second derivative, which is what we actually need, is lambda squared e to the lambda t. Fair enough. Now we can sub that in to the equation, which I'm going to call the dE, or the differential equation. The mx double prime, I'll write out the whole equation as is for now. And we're going to take this for our x double prime, and we're going to take this for our x. That's what they were, and that was the consequence. So we're going to have m lambda squared e to the lambda t must equal negative k e to the lambda t. Perfect. Now, one of the things we can do is divide immediately through by e to the lambda t, because exponentials are never equal to 0. And so what we end up with is lambda squared equals negative k over m. And I'm just going to take that to the next page. Lambda squared equals negative k over m, or lambda is equal to the square root, positive or negative, of negative k over m. And so already we should be a bit suspicious. We have this negative inside the square root sign. But if we just factor that as negative 1 times k over m, then remember square roots can apply to each term individually. So we're going to have plus or minus I times the square root of k over m. So we have a solution. E to the lambda t is a solution if lambda is equal to one of those two values. Well, that means our two solutions are x1 of t is equal to e to the, big brackets here, positive I square root of k over m. And remember, it's e to the lambda t. This is our lambda, and then we have a t at the end. And x2 of t is equal to e to the negative, let me erase this, that was positive but it wasn't very clear, e to the negative I square root of k over m, close the square root, times t as well. Either one of these, if we sub it into the equation, will satisfy it. Now, if you were following pretty well with the complex exponential and you see this time in here, you should be thinking, oh, this is something rotating around the complex plane. It's going like this, it's going like this over time. And this one is the same thing but rotating in the other direction, as it turns out, because we have a negative angle effect with that. But that's less obvious, I think, especially at this stage when we're new to things. What we're going to do instead is use Euler's formula to break this explicitly into sine and cosine terms. x1 of t, which was our e to the positive I square root of k over m all times t, is the same as cos of the thing beside the I. It's I theta, but the cosine just has the theta in it. Square root of k over m times t, plus I sine of exactly the same thing here. There we are. That's lovely. x2, by comparison, is almost identical. In fact, we're just going to tweak it a little bit. It's just the same thing but negative. And so if we actually group this a little differently, let me put the I out front, and then all of this times that with a negative, that becomes our angle. And so we get cos of exactly the same thing but negative, and plus I times sine of exactly the same thing but negative out front there. This is absolutely true. It's just a bit awkward, so I'm just going to do one little thing here to tweak it. The cosine function, this is all real now, this whole cos thing is all real numbers. When we put a negative or positive angle, we get the same thing back because cos is symmetric around the center. So one of the trig identities that comes with that is we can just use the positive version of this function for cos. So this is equal to this for cos. For the sine function, its relationship is a bit more interesting. It's called an odd function. If I had a negative angle and got a negative thing back, if I use the positive angle, I would get the same thing but positive. Oh, if I flip the x value sign, I also flip the y value sign. And what that lets us do is basically take this negative sign out front for the sine function. So this would be negative I sine of square root of k over m times t. Not a huge deal, but it just makes the two solutions that we're seeing here more directly comparable, because now they have the same angles inside, and any differences are just about the multipliers outside. It's a little easier to deal with. So that is our second solution, x2 of t. And that's essentially what we blocked through on here. And what that lets us do is find the period of the oscillations, because now we have our system back here. In fact, I'm just going to copy this guy over here. one building block. That's what we got with the symmetries here. And just looking at that or its matched thing for x1, how do we find the period of any oscillations with cosines and sines in it? It's equal to 2 pi divided by the multiplier inside of the time. So it's 2 pi over square root of k over m. That's a lot of fractions. Let's turn it upside down. That's 2 pi square root of m over k. Actually, we had found that in an earlier lecture. Just recall the other observations that we had, which was larger m's, larger mass, implied longer period. There's more inertia, harder to move. Whereas if we had doesn't look like an m, larger m here, larger k, a stiffer spring, that sped things up. We got more acceleration, bang for our buck for every bit of motion that we had. And so that led to smaller periods. And we can see that here. The bigger m is, the bigger period is, the bigger k is. We're dividing by bigger numbers, the smaller the period will be. So this analysis is what you're also going to see when you take your second year differential equation course, so keep that in mind. We assumed a simple form for the solution, and it happened to turn out that the lambda value in this e to lambda t ended up being complex, but that was okay. We could just work with that, assume that that's totally viable. And it got us down to solutions that were built on cosine sine functions, which again is what we expect for this spring mass system, where we expect to see oscillations. The one fly in the ointment is this I value. We're going to deal with that next.